just in the last week or two, there's been a new catalogue based on the Gaia data, which has got, I think it's about 60,000 of those stars with decent orbits, and it's my intention to make that data set available through Occult.
That'd be great.
Yeah, that will be a good development. Okay, well,
We had-
Dave
Yeah.
Herald, it is your turn for the next talk. We really need to move on. And so Dave, we understand you're going to talk about what happens to an observation after submission. And I'll appreciate it if you start that.
Yes, I've just got to figure out how to, sorry about that, I need to share my screen. Your screen. Okay, and people can see the my opening slide, I hope.
Yeah, we
Yes.
see it.
Okay. This is a topic which it's an important thing. It's great that we go out and make these observations. We're excited and we report them. And then the issue is what actually happens and then position. And there's been a couple of things said today and yesterday, which hopefully this presentation will touch on and show where we're good and where we're pretty lousy with dealing with our results. So you go out in the field and you make your observations, and that means you're one of the people on the left-hand boxes here. And with great enthusiasm, you record you analyze your recording, and then you send it off to the your local regional person, and they do something with it and put together results which typically appear on a local website, the North American website, Join in Japan. That's the arrangement in the US and in Europe and here. When you submit the observations, what actually happens there? And this is a straightforward bit. Most people probably have a bit of an idea here. The regional coordinator, they get multiple observations coming in, a mountain of files, I guess, and somehow they go through that and they bring all the observations together to create a file which contains all the consolidation of all those observations. In that process, inevitably they'll be looking for any problems with the data, things which don't look right, and have communications with the observers to resolve them or try to resolve them. That can go back and forth, can be time consuming. In addition to that, which is probably the main bit that people sort of see happening, the regional coordinator will generate a post-diction line to put in the event file, and that's so that we get a coarse indicator of whether there's something really anomalous there. It's a good indication of, hey, if there's a huge difference between the post-diction and an observation, question is, well, why? And that can lead to chains of communication about, is it a good observation or not, to confirm it. Fit an ellipse or something else to the observations. And that's part of measuring the size and stuff. Have a go at fitting the observations to shape models. I think most of the regional coordinators are not highly skilled in doing that. When you've got a double star involved, there's do a double star analysis, and that can be complicated, and sometimes there's interesting challenges in making sure that you've got a consistent identification between primary and secondary stars between the observers. Initial asteroid satellite analysis. In this presentation, I'm not going to spend any time on dealing about satellite analysis. There's some fairly rigorous processes we need to go through with that to be satisfied that it's a satellite rather than a double star, which is causing the issues. And then you've got the issue of some events across multiple regions. Europe and US is fairly common. Europe and Japan is not unusual. Australia and any other region is not common, but it does happen. I observed one event, or tried an event where somebody in Spain would have been able to see it as well. The Adelheid event was between Australia and Europe. So, and that requires some level of coordination between the regional coordinators so that the data gets collected completely in one location rather than having it split across multiple locations. So this is probably the step which we're getting into areas where level of knowledge of what happens is probably not so good. So on the left-hand side, we have the various sources of information, the 5 traditional regions, plus Unistellar's come in recently, and we've been getting results from there. Regional coordinators put their observations together, and then they send them to me. Ideally, we like to have the observations come from the regional coordinators within about 2 months of an observation of an event occurring. We need to have reasonably, in the ongoing sense, we need to have reasonably quick processing. One of the reasons for that is if you take 6 months to report an event, chances are if there's any problems with it, you've forgotten all about it. And if you've got to coordinate a funny result with other observers, everyone's forgotten about and creates a lot of grief. And people forget about doing whatever's required. So in the reporting process, people should be reporting to their regional coordinator within a week or so of the observation, and with the aim of the regional coordinators pulling them together within 2 months and forwarding them on. So they forward them on to me. What happens? The process is essentially a quality assurance process. When I receive the report and process them, basically the level I look at it is relatively superficial in the first instance. Prima facie, the regional coordinators do a damn good job, and it is not common that I have any significant concerns with the overall data that comes in. In that, the other thing that I do, there's the shape modeling, double stars and possible asteroid satellites. Those are issues which don't come up. Well, double stars and asteroid satellites are not common. Shape models, there's a whole heap of issues around there. They're issues which are not straightforward and routine. And myself and Dave Galt have a close look at those and settle down what the results of the model, those sort out the a final result for those various issues. We also look at chord consistency. I spoke yesterday about situations where chords look odd. One, you see chords which seem to be displaced from when you compare them with adjacent chords. And I think Kevin's presentation, he had with Adelheid, there were one or two situations there, if you notice, which most probably wouldn't, where you'd have to wonder whether some of the chords had a time-based displacement. That's a significant thing in if you've got a chord which looks rather differently located to other chords. The fundamental question is that a real location, or is there a measurement issue involved? And here we have the issue of, if it's a real displacement, it's not to be expected because it's an unusual thing. And if you're going to say what I have observed is unusual and different from what is expected, then you need to be in a position of being able to substantiate that your observation is valid and real. And for that purpose, in that process, you need to be able to answer questions about the reliability of your observation. It's not just a question of, I observed this, believe me, I am right. The question is, I say I've observed this. Question, well, show me, address these issues. I'd like to see your light curve to make sure. Various other questions can arise, and there's an expectation that observers can substantiate odd observations. And I emphasize this because it's not so common now, but I've had situations in the past where some observers take the position of, I've reported this, how dare you question what I have reported? And I've had some people very strident on that. And in terms of scientific process, that's just unacceptable. Unistellar, they're a relatively new group on the horizon. They've got a global network of telescopes, citizen scientists. They operate independently of all of our regional coordinators, and there's good reason for that, and it's something we've in fact encouraged to operate on that basis. When their observations come in, I've merged them with the existing events where they are additional observations, or create new events. Finally, as I've just touched on this, where an observation looks interesting, if I can put it that way, where there might be hidden problems, ask questions. And that comes up particularly with asteroid satellites. There's questions to be asked there. But displaced chords, there's no very simple way of saying this is what we look for, other than this observation looks interesting, odd, unexpected, unusual, whatever. We'll ask questions. And when we get through that process, the observation gets added to the main file. I would say that in 95% of observations that come through, the time that I spend on doing everything in that orange box in the center would be somewhere between 1 and 3 minutes. On the other hand, if there's something where there's something seriously wrong or seriously unusual, then the amount of time that could be taken could be 10 or 20 man hours with going back and forth and debates and whatever. It's a case of 2 or 3% of observations occupy 95% of my time. Now, the next step, I put the observations into the main file on a regional basis. They come through. Then when we have all the observations for events in a month complete, then Dave Galt does a second level of quality assurance. He goes through that month's worth of observations and reviews them independently, picks up errors that I've made or things I've overlooked, and it's just a final quality assurance to make sure our data is fully reliable. So we have all these observations. We put them into our database. Is that the end of the story? Is that all we're on about? Well, no. We're doing this as to try to achieve some ends to it. And here are the 5 topics that I'm not going to touch asteroid moons because that would take too long to go through that. But I'm going to go through the other issues here. First thing, size and shape of asteroids. Going back to the 1970s, I think, when asteroid occultation efforts got seriously underway, and really didn't get, probably more like the 80s. The original motivation for attempting occultations was actually to get a measure of the size of asteroids, because at that stage, their size was guesswork. We didn't have any satellite measurements such as IRS or NEOWISE for their diameters. They were a big unknown. And back there, in those early days, the prediction accuracies, we've got an event going through Washington, but maybe the uncertainty will put it down over Chile or Antarctica. Uncertainties were huge. One of the challenges with measuring the size of an asteroid is that a single chord will only give you a minimum diameter. You need to have multiple chords to measure the diameter in any meaningful way. So the majority of our observations we do these days, which are single chord observations, are not very useful for measuring the size and shape of the asteroids. Certainly not the shape. There is a serious overall difficulty with the occultation process for measuring the diameter. And that is when you observe an occultation, you are seeing just one profile of the asteroid. Most asteroids have got some form of oblateness and significant irregularities. And if you're only getting one view of that, then your ability to get a reliable diameter is restricted. And that's an ongoing issue. However, with the shape models, which Kevin's spoken a little bit about, combine our occultations with shape models and we can derive good diameters. Shape models generally developed using light curves, on the whole measured by amateurs, different area of amateur work. But we get good diameters when we fit our occultations with the shape models. Shape models are interesting in that they give a reasonable representation of the overall shape of the asteroid, but give no information whatsoever on the size. They're totally scale independent. An occultation observation gives no information on the three-dimensional shape of the model. But when you combine that, the profile that you get from the occultation measurements with the shape model, you can measure the diameter of the shape model that fits the occultation observations. And I'll just note briefly here the issue with diameters. What's the diameter of a house brick, which is nice and rectangular. In this area, asteroids are irregular, similar thing like a house brick. There are two ways of specifying a diameter. One is a volume equivalent diameter, and that is a diameter of a sphere having the same volume. And the other is a surface equivalent diameter, and that's the volume of the diameter of the sphere having the same surface area. And we've been consistently working with a volume equivalent diameter because that relates back to being able to measure density. Now, one of the uses of our occultation results is the shape modelers use our occultation data to improve their models. Joseph Jurek and his team regularly access the occult data file to extract observations to merge in with their data sets. One of the things we've been able to show, and that was dealt with that in the monthly notices paper we published a couple of years ago, the occultation results established that the diameters which have been measured by the satellites such as NEOWISE, AQA, and IRIS are quite reliable. Where there are significant differences, the likely cause is an unexpected difference in the albedo of the satellite, its reflection. But this next bit, how do we go publishing our results? We make all these measurements of their diameters. What happens with them? Well, publication results, we have been pretty bloody awful at it, to put it simply. Pardon my language there. It's like a lot of things that we do when it comes to publication results, we are not good at it. The paper that I wrote some years ago at monthly notices, we gave an indication of the results we were getting, but no more. As I'll be touching out a bit further in this, an archive in the planetary data system, I've created a full table of diameter results for asteroids that have shape models. And this is the first time, to my knowledge, that there's been any effort to actually put our diameter measurements out there on the table for all to see. I should note here that my view of what we do is there's no point in us doing it unless we actually get our results out there amongst the global astronomy users. And it's that step in our overall process which is our lowest level of performance as an organisation. A final note there, the diameters we're getting from asteroid occultations. Some years ago, there was a paper published where the reliable diameters we're getting from our results combined with diameters obtained from other sources have been used with estimates of asteroid masses, which they derive from the gravitational effects of asteroids on other asteroids in changing orbits, to derive the density of some of the asteroids. This is an indication of the data that can be extracted out of a cult from our data set. Left-hand column there is the asteroid number. The next set of columns, 3 columns there, is the asteroid name, and then the diameter and the uncertainty. It's a weighted mean of the values from the 3 main satellites. And then there's a series of columns that I think there's either 5 or 6 groups of columns to make sure we cover all possible shape models. But going through this one where I've got the highlighted columns there, the first 2 columns gives the diameter and its uncertainty, so that, and I'm going to pick, I'll pick the first one there, Julia. The asteroid measurements is 145 plus or minus 7. From our observations, it's 137 kilometers plus or minus 3. So it's somewhat smaller than the asteroids. And that result is a combination of 7 separate events. And that's measured against the DAMIT model 1805, which is a relatively recent model. If you go over to the next column, that gives 140 plus or minus 2 kilometers, so a bit larger. It also uses 7 events, but it's a relatively old model, DAMIT model number 293. Now, if we go down that column a bit to 94 Aurora, here we have the satellite determination 184 plus or minus 10. With the first group of columns there, we've got 194 plus or minus 5 from 9 events. But the next column has got a 1 in it. And that says we used 9 events, but there was another event which doesn't fit that shape model. So it's a concern about how reliable that shape model is, but it's a low level of concern because there's only one of the events was flagged as being an invalid model. You go over to the next column, and here we have 187 plus or minus 9. And for that one, we've managed to use 16 events, with none of them being flagged as invalid. I won't go any more of that. That's sort of indicating what we can get out of our data set as a whole, and the type of results, in my view, which we need to be putting out there, as this is a primary result from all our efforts. So I'll move on from there. The next bit is astrometry. This was not an original aim of the asteroid occultation program. It came about, I have a background doing a lot of astrometry with comets in the 80s and 90s. And in 2003, after an IOU conference in Sydney, there was a separate meeting about asteroids, where the director of the Minor Planet Centre, that was Gareth Williams, he was there, and I had a discussion with him about what we were able to achieve with asteroid occultations. He was very interested in that, worked with him over a couple of years and developed a process where we could feed our results to the Minor Planet Centre and included in their data set. The processing that was put in place was outside of the usual processes. Gareth Williams had his own personal bit of software for converting our results into something that the Minor Planet Centre could use, which is in the long term unsustainable. Anyway, we reported observations consistently for many years. But around about 2019, we started realising there were some issues with our data set. There were issues with problems of past observations where when we looked at them, things way back which we thought were good, we compared them with the JPL orbit, not good, and conversely, observations which we thought had to be in error turned out to be quite good. A range of issues with the overall data set. So we started a process of reviewing everything in the data file. Around that time, there's also the Faithon event, which I got into discussions with Davide Farinocchia at Horizons, and an extremely valuable couple of years, and I mean years, working through the fine details of the analysis of our observations to get an accurate astrometric position with an appropriate set of uncertainties. And I'll mention a little bit more about that in a moment. Then we've had the minor planet centres updating their systems at various levels. There's been a new International Astronomical Unit standard called AIDS, Astronomical Data Exchange Standard, which all new observations have to be reported against. That standard accommodated occultation type observations. They get stuff from radar and various other things which fit into it, sort of. But in the process of working through that, we had to have the aid standard revised to add a couple of new categories or fields, definitions, to accommodate the certain aspects of the high precision that we obtain. And in all of that, we have a new observatory code allocated, Minor Planet Centre. Every person that submits observations, they have an observatory code for their location. We have an observatory code of 275 for non-geocentric occultation observations. I won't go into the explanation for the non-geocentric now. Reporting is now recommenced. I sent off the report in April, May. Minor Planet Centre still has implementation issues. I'm hoping that this full moon we will have our first batch finally processed, and for the future our results will be Main Street processing. The other aspect is when we've got special events such as Faithon, Didymos and so forth, we have ability to report directly to the Horizons people, and we're in the happy position with Didymos. You could have an observation one day, results get through to regional coordinator, they send them to me, I do my little bit there, and within an hour or two of me having processed the observations, JPL could be in a position of updating their orbit. Because of the work that we did with them on revising our error models and so forth, they have high regard to the accuracy of our data. Very high regard. Just briefly, what's the basis of our reports? It's a little bit unusual, and it came out of my discussions with David Farinocchia. The little graphic there I took from a book about solar eclipses, but it's exactly the same. You got the star and the asteroid cast a shadow on what's called a fundamental plane. It's a plane through the center of the Earth, which is normal to the direction of the star. In our observations, what we actually measure is the point where the axis of the shadow intersects that fundamental plane. I should add here, in terms of the types of precision we're dealing with, the time of every observation we come through actually gets adjusted to a later time, only a small amount later, but the later time by the light travel time from your position on the surface of the Earth to where the shadow appears on the fundamental plane. It's usually, well, it's always less than 0.1 of a second, but that's the type of accuracy we're dealing with. The notional time for a photon to get from you through to this plane on the Earth is a correction which has to be applied to every observation. And it's different for every observer on there. The actual astrometry that we report is the X, Y, Z coordinates, the three-dimensional coordinates of that point on the fundamental plane where the shadow axis intersects it. The curious thing is the reporting mechanism is exactly the same as if you were doing positional measurements from a satellite orbiting the Earth or orbiting the Sun, except just imagine it, our observations are based on a satellite orbiting inside the Earth. It's a little bit interesting. Here's an example of the astrometry report that we send. This is the one I sent this month, which is the back file thing. It's got some stuff up here identifying who we are. A list of measurers, which are the regional coordinators, and there. And then a list of observers for this first batch. There was about 3,000 observers. It wasn't 300, but it was thousands. And here's the positions. You've got the observation, the identification of the asteroid, occultation, our observatory code, the event time, RA and declination of star. Ignore those. That's referring a reference frame measurement. That's saying it's centered on the Earth. And here's the X, Y, Z coordinates that reporting. That's the decent bit. Here's the uncertainties in our measurements. That's in arc seconds. So this one, it's 3.4 milliarc seconds in right ascension and 5.3 milliarc seconds in declination. This one here, which is a series, it's must have been a single chord observation there, 251 milliarc seconds. Huge uncertainties on that one there. Catalogue here, shape occultation. This value here is a value which we had to have the AID standard updated for, where there's a one there. We're actually reporting the position of the center of mass of the asteroid, not the center of figure or center of light. That was something that was provided for radar observations, but not for our optical observations. And positions there of the uncertainties in the star position. And this column here is a reference to our error model. And you also see here the RUWE value when it's large. I won't go through this at all. This is the parameters of our error model, very complicated. And it's in the occult help file there. There's a raft of different possibilities in there. It's a complex error model, but it gives very good results. Now, how good is our results? These are the results from the Didymus observations. The table here shows the observations we used. These came from the Didymus team at NASA, JPL, or wherever. Each of the ellipses over here represents an observation, the uncertainty limits of an observation. And I think this was this dot there with that big circle. That was for the first of the successful observations. And all these, the ellipses indicate the uncertainties of observations, and the center is where the best fit is. And you can see they all sort of overlap somewhere in this region. Notice that they don't all overlap. There's not a clear spot in the middle. It's sort of somewhere in there, which is an indication we might think we're getting very precise results, but they're not quite so precise as some might think. These two ones with dashed, they're ones where we're fairly sure there was a problem with the star position. Now, I said here the high credibility of our observations. I want to emphasize here that one of the issues with the credibility of the observations is our quality control mechanisms. Our ability to question things which don't look right. It's a critical bit of ensuring our observations are treated highly reliable, that we actually ask difficult questions on observations which are which deserve having critical questions asked. Now, this is an interesting indication of just how valuable our results are. These are the accuracy measurements associated with the DART mission. This blue circle indicates a position where the asteroid was supposed to be relative to a particular orbit. Using all the observations, all available observations prior to some days before the mission impact. Quite a large, it's sort of, that's in kilometres, it's 4 by 5 kilometres. The orange circle here is the how that circle was reduced as a result of including some radar observations. And it was the result of the radar observations which allowed successful occultation results. And that had the centre there. This orange, this yellow circle, that's the position of the asteroid used from the DART system, operational navigation system. In other words, what they're able to extract from knowing where the DART satellite was. And this little purple circle, ellipse here, is the results of our asteroid occultation efforts. As you can see from there, our uncertainties are incredibly much smaller than any of the traditional methods of getting accurate positions. We're looking at this uncertainty of the order of less than 100 meters in the position of the Didymus location. And it's this type of thing where we have, working with Horizons and with NASA JPL, that credibility in our occultation results has become well established amongst those that really matter. Moving on, because time's moving on, double star discoveries. We get a small number each year. We make a discovery, it should be recognised with an entry in the Washington Double Star Catalogue. It's almost certainly the Washington Double Star Catalogue. There's also the 6th interferometric star catalogue, which is our data. That's generally for spectral interferometry and the like. Our data finish up in the Washington Double Star Catalogue. The process for getting our results into the Washington Double Star Catalogue, it's not a case of us just sending our observation results to the United States Naval Observatory. The process, and USNO has insisted on it, is we have to have our observations and results published. And the recommended journal that they recommended was the Journal of Double Star Observations. It's very easy they're very easy to work with, straightforward process. It used to be managed by Brian Loader of New Zealand, but age has got the better of Brian. I think he's probably getting close to the 90s by now. And he had to stop doing that a couple of years ago. And where are we at now? Well, the current situation is a black hole. We get these observations, we enter them into a cult, and is the information getting out and getting published into the Washington Double Star Catalogue? The basic answer is no, which is a huge oversight on IOTA as a whole. In order to have our double star observations properly recognised, we need to have a paper published. Now, I suspect most observers are not comfortable with writing papers, tedious. Hey, well, I like observing. Why do I have to sit down and write a bloody paper? Thing with what is required is in quite a basic format. The basic information is quite straightforward. You need to have a light curve or multiple light curves if you've got multiple observers, which show the step events. You need to be able to identify the star with its magnitude, location, identify the asteroid, and the date of the event. That's basic bibliographic evidentiary details. Then you need to have the actual measurement results. That's not so straightforward. A cult will do it for you, but you need to know what you're doing. But that's an easy thing where people can assist you with that. So basically, observers have most information required, and my view, I'll emphasise it's my view, if we had a standard pro forma paper, it would enable observers to easily prepare a paper for publication. And this would include observers in countries where English is not a native language. They could have the knowledge that the text of the paper was reasonably good English, and all they've got to do is put in the observations data. All that required there is that the observer with a pro forma paper will be able to add their specific information in there, have a bit of support to actually get the double star solution, and you got a paper. And an important thing is here, regional coordinators generally don't have the spare time to go through and handle the double star observations, discoveries. Maybe they do, but maybe not. And what I'm suggesting here is that someone does the work to create a pro forma paper. Probably need 2 or 3 papers to cover the 3 possible solution types. And there are already a reasonable number of papers we've had published in the journal Double Star Observations, which they can be readily used to establish a template. Then observers that are involved can use their data to populate the paper. Coordinators or whoever provide assistance have a process where the paper gets reviewed by a coordinator or somebody who takes on that role and submits the paper. This means that double star discoveries, and they're always discoveries that we're finding, people will get due recognition for what they've discovered. But it does, what I'm suggesting here, the recognition should involve the observers because, hey, we've made this valuable discovery. I want to have some recognition for it. Well, all I've got to do is fill out this paper and then it'll get into the Washington Double Star catalogue. Yes. Okay. Final bit I want to get into is archiving. It's all very well as having this data set, but how do we make sure it's out there in a public place where it's got longevity and it's not just stuck in an obscure bit of software called a cult, which most professional astronomers wouldn't be aware of or whatever. Now, our data set gets archived with NASA's planetary data system, a particular part of it called the small bodies area of it. David Dunham made the original arrangements to get our data set handled there. We've been archiving basically on an annual basis, but that's been paused for several years for the same reasons we paused this astrometry. The next archive is almost ready to go. A lot of work's needed in putting this archive together, and it's background work. It's in a cult. I've built the code necessary to create the files, and I've also created some what I call header files, which give required descriptions for every field. Now, just to keep things in context, for asteroids, in each event, there are 260 columns of data, and there's over 8,800 rows of data. That's 2.2 million data items. And that's just the description of an event. Within an event, there's all the individual observations, and each observer, there's 42 columns of data for each observer for an event, and there are more than 36,000 rows of data, which gives you 1.5 million data items. So the archive, that's 3.7 million data items, and each column, and of that there's over 300 columns, is required to have a full description of its content. And here's a bit of an illustration of the data. It's only a small part of it. Over here you got the observation date, a reference 0 time, a star number, star catalogue identifier, the number in that catalogue, that's a Gaia version number, a Gaia number, stars right, essentially keep on going on. On the star catalogue, put the cursor on the text up here, and you get the explanation. And the star catalogue, which it's got one of the longest explanations, is it's the type of information that has to be specified. So here's all the references for the catalogs we're using. So fair bit of work putting all that together, and still doing some final revisions on that. And if anyone feels like assisting with reviewing for the descriptions for being up to date, please let me know. I'd welcome your assistance. The archive file content, the observations, diameter shape model fitting, astrometry, and also double star results. And that's it from me. Any questions? Hang on. My
Well, David, I want to thank you for
my
very
apologies,
informative.
my headphones battery
Sorry?
went flat on me, so I haven't heard what you said the last little bit.
David, I'm just wanting to thank you for a very informative presentation, and that's very useful information. I'm hoping that you're going to get some volunteers to help you with some of our holes in our data. So anyway, in the absence of specific questions, let's move on.
Well, hello.
Hello.
Wolfgang Beisker and Toyota ES, and I would ask, there's a lot of archiving, what you just demonstrated, Dave. But do you feel that we actually should archive all the images from the people? Because, you know, the analysis of black curves depends very much how you set the apertures, how you set the model of fitting of the star magnitude and so on. So we feel the only thing really to keep the things forever for the future community would be to save the original images. What is your opinion to this?
You could ask that question for any scientific observation, and the reality is in the professional world that's not going to happen. If you report traditional astrometry, you take a CCD image, you measure it. Is there any expectation that people maintain the raw image? Well, no. It's in this area where, when I've been trying to encourage people to provide their base light curve. You've seen a couple of images there, and you see me plugging away, because that gives you a clear indication of what the observer recorded. And if you go through the light curves that are available, I'd have to say that some light curves, you look at them, you think, oh, geez, that looks a bit suspect. Other light curves, the majority of them very clean. My view is that we should be retaining a basic record of the light curves, maintaining the video behind it for the detailed measurements behind it in long term. It's the amount of data that's involved, it's just too great for any sensible long-term archiving, in my view. Whereas, I mean, if you take the little image files I've maintained for the light curves, they're about 1 or 2 kilobytes. The CSV files that people generate can be half a megabyte. And of course, if you go to AVI files, you can be talking about gigabytes. It's all a matter of being a pragmatic assessment of what is valuable in the long term. And nobody's going to go back and, hey, I want your light curve, your data from 20 years ago, so I can remeasure it. for this one event. You need a sort of a big picture view of what are people going to do with the data set and what is the importance of a single event in the big picture.
Yeah, thank you. That was just a discussion inside the board of Jota ES that maybe we should save all the images. But the problem is, of course, that many people don't want to supply it because it makes more work to them. And also we have found people who archive this all, who comment on this and so on. So, but this is just a discussion which is going on at the moment at Jota ES. And we will have some discussions on this on the next ESOP meeting in Armagh in Northern Ireland, which will take place in September. And I just want to know your position on this. Thank you.
Well, thank you for your insights, David, and thank you for your questions, Wolfgang.